this is something that we are quite familiar with. If we want to know what's the temperature now, just find a thermometer. A thermometer would usually be made of a piece of glass tube, and it might have a little bulb at the end, expanded region with some liquid. It can either be a silvery liquid, which is actually mercury, or it can be alcohol, which is colored, given a red dye so that it looks red. Okay, and you would see this bulb with this liquid inside the bulb at the bottom, and then you see a tiny line, either a silver thread of mercury or a thread of this red colored alcohol that goes up and down. All right, if it gets warmer or when it gets colder. And of course, you would see markings. You will see markings along the glass tube, either on the glass tube or maybe on a strip of paper or plastic next to the glass tube that tells you what the reading is. So, for example, there might be a line next to it. This glass tube might be attached to a piece of wood or plastic, and on that plastic piece there would be lots of markings here. All right, that tells us with numbers between them to tell us the temperature. Like, let's say that might be 0, that might be 10, that might be 20, that might be 30, and so on. Right, so and it might be in degrees Celsius or Fahrenheit, depending on where you are. Okay, so that's simple enough. Okay, but I want to ask this question. Now I want to ask this question about whether this is accurate or even whether it is meaningful. So let me start with the question of whether a thermometer is accurate. Now, why is that a question? Okay, I can think of a simple reason why it might be a question, because the thermometers that we are familiar with, okay, of the thermometers that you might have seen, there are already two kinds. That there is the mercury kind, where you have this silvery liquid in the glass tube. There is the alcohol kind, which is usually colored yellow. Okay. Now, today with all the new technologies, you might even have seen others, like a digital kind that shows a number. You might see it in some cars, for example, or there might be a special kind, infrared kind that people might use for babies, shining some infrared from a special thermometer, and then you see the number digitally. Or there might be a kind that uses some colored dye, right? So that changes color with temperature. So there are all these types that we can already actually see around us. Okay. Now, are we quite sure that they are recording the same values? Okay, perhaps when they are measured against one another, checked against one another, we can always find out whether if we use maybe take a mercury and alcohol thermometer and put them together, we can see whether they're measuring the same readings. Now, and in science, in physics and engineering measurements, there are also other kinds where we make use of the resistance of a piece of wire, because resistance changes with temperature. Okay, now that's fair enough. You can say that you compare those and you check whether they agree. So that's simple enough when we are talking about things that we can hold in our hand and that we can see with our eyes. But that is only possible within our existence in everyday life, meaning within maybe a temperature of between maybe 0 and 50 degrees Celsius, where we can live and work. That's where usually these computers are made for. What about temperatures that is at minus 100 degrees or 1000 degrees, right? Some of this thermometer would probably vaporize at those temperatures. In that case, we need other technologies like maybe resistance thermometer, or there's something called thermocouple as well, which involves twisting two pieces of wires of different metals together and producing a voltage, and that voltage would change with temperature. So there are all these other kinds of thermometers, and you can we would use them at different temperature range, temperatures that might be too hot for us to live in. Okay, that's fine. But so for these other ranges of temperature, how do we know if they are correct? We can't really check against these familiar temperatures. So what this means is that thermometers and measuring of temperature is very much dependent on the properties of materials. Now, what I want to do now is to look at how temperatures are normally calculated from the property of the material. Now, in this case, for mercury or alcohol thermometer, that would be the length of the liquid, this thread of liquid. For resistance, it might be measuring the resistance. Thermocouple, it would be measuring the voltage. So, and there is a usual formula that we would use for finding the degrees Celsius. Right? The degree Celsius. So if I start with this using of the thermometer, the glass thermometer for measurement. Now, the way it is done, is actually already suggested by the markings. How are the markings made? For example, now the way the markings made are quite simple. Basically, this thermometer is first placed in melting ice. Okay, and when it is cold, the liquid will contract and the thread would come down to a certain level, and that level for melting ice would be marked as the 0 degrees Celsius, and then it is placed in boiling water. Okay, and the thread will go up to a certain value, to a certain length, and that position would be marked as 100 degrees Celsius. Boiling water. Okay, so that would be marked as 100 degrees Celsius, and in between it would be divided into 100 intervals, and that's how we have our 0 to 100 degrees Celsius. 100 degrees Celsius. Okay. Now, what I want to what I want to explain is how this idea is actually used when we have other materials like resistance and, in this case, voltage that is generated by temperature change. Okay, the idea from here, all right, I've explained it physically and how this is actually done physically, but we can also think of this idea as a formula. Now, and that formula is this. We would think of, let's start with the eyes, marking of the eyes. Now, instead of thinking about putting a mark there, let me think about measuring the length of the thread when it is at eyes points. Let's say this is, I'll call this L0. Now, and when you put it in boiling water, it becomes longer until there. So it is now longer. The length of the liquid thread is longer. Let me call that length 100. Now, if I want to know or find the temperature when it is at a certain length, right, imagine for now that I don't have these numbers. So let's say the liquid comes up to here, for example. So if I don't have these numbers, what I can do is I can find the length, measure the length of this, let's say I call it L. Okay, I know that in between this L0 and L100 is divided in 100 markings. So what I can do is this. I can make use of proportion. I can find the increase in length between eyes point and here. So I'll call it L minus L0. So that would be this length. Okay, and I find it as a fraction of the length between, or of the distance between boiling point and ice point, and that would be L100 minus L0. And I divide them, right? That's my fraction. And so this as a fraction of this distance, and I know that since we have a scale from 0 to 100, all I need is to multiply this by 100. It's like finding percentage, right? And the answer would be the value of the temperature in degrees Celsius. Okay, I use the symbol theta for now. It's like the Greek letter for T to distinguish it from the capital T, which we often use for Kelvin in this topic. So that's the temperature in degrees Celsius. That's how we might calculate it if we don't have the markings. All right, and in fact, the markings, you can think of the markings as equivalent to this mathematical idea. Now, if I now want to use this idea to find the degree Celsius when, say, the temperature is 1000 degrees or when the temperature is minus 200 degrees, what I can do is, well, I can't use the mercury anymore or alcohol because it's just going to freeze at minus 200. Nothing is going to move, or it's just going to burst up when it goes to 1000 degrees. So I can use a resistance thermometer, for example, by measuring the resistance of a piece of metal, usually platinum. I can, by measuring how the resistance changes with temperature, I can use the same formula to calculate the degree Celsius at 1000 or minus 200. So that means that instead of the L, so it's quite simple, as in I can rewrite this quite easily, meaning that instead of measuring the length of a liquid, I can just measure the resistance. So I would, instead of L, I would be measuring the resistance at a certain temperature, high or low. But before that, I must first measure the resistance of that piece of metal at ice point. I'll call that result R0, and I must also measure this resistance at boiling point. Just put it in boiling water. Okay, and then I can put it into this formula, multiply by 100, and I would get my temperature in degrees Celsius. So that seems simple enough, but now we need to ask the question, What if I want to compare these two results? Okay, I can't bring the glass thermometer to 1000 degrees Celsius, but I can bring my resistance thermometer down to our room temperature. Okay, so I can measure the resistance at room temperature and calculate the temperature, and then I can compare it with what I get from my mercury thermometer. Question is, will I get the same answer? And the simple answer is no. The reason is because the resistance doesn't have to change in a way that is proportional to, say, the temperature that we measure using the glass thermometer. Okay, and in fact, if you plot the graph of the resistance against the temperature that you measure using the glass thermometer, you won't get a straight line. Okay, so it's not, we wouldn't expect that anyway, because the resistance can be a complicated thing. So in general, those two are not equal. Those two answers would not be equal, simply because resistance don't change in the same way as those two are not equal. Resistance don't change in the same way as the length of the mercury. So what this tells us, what this discussion tells us, is that when you measure temperature, the result depends very much on the properties of materials. And that is a problem. That is a problem with measuring temperature. And is it possible to have a way of measuring temperature that does not depend on the properties of anything? Right? That seems hard to imagine, because if it doesn't depend on property of anything, then what thing do we use to measure the temperature? I'll talk about that in the next video.